Good day, viewers. You are welcome back to Tindanious Maths and Science Tutorials. If you are new here, kindly subscribe, share, like, and comment for more interesting videos. In today's YouTube session, we are going to prove the Euler's formula using the Taylor series. In our previous lecture videos, we learned how to prove the Euler's formula without the usage of the Taylor series. So before I proceed, let's note this. Exponential x, or e to the power x, is equal to 1 plus x plus x to the power 2 over 2 factorial, then plus x to the power 3 over 3 factorial, plus x to the power 4 over 4 factorial, plus x to the power 5 over 5 factorial, then plus, then it continues in that way. Okay, so you have indefinite number of what? Of either x terms or what have you. Okay, so let's look out for the Taylor series expansion for sine x. Okay, so for sine x, the Taylor series expansion for sine x is equal to, we have x, then we have minus, then x to the power 3 over 3 factorial. So if it begins with plus, then minus, then we have plus. Okay, but note for the sine function, okay, for the sine function, the powers is let's say it's odd. Okay, not even. Even is for cos, whereas sine is for the odd is for the sine function. So 3, then have x to the power 5. Okay, over 5 factorial, then plus, let's say x to the power 7 over 7 factorial. Sorry, we have negative plus, then here becomes what? Negative. Okay, then plus, then have it that way. So the Taylor's series expansion for cos x, we have 1, then minus, then we have x is even, so the powers, okay, they are even, so we have 2 over 2 factorial. This is negative, then we begin with for positive, then plus x to the power, then 4, then over 4 factorial, then have minus x to the power 6, then over 6 factorial. They get that way. They have plus, then they have indefinite number of what? Of the x term. Okay, so this is, so note for the cos function you have what? The even powers. Okay, and for the sine function you have what? We have odd powers. And for the exponential function we have the combination or the mixture of what? Of both even and odd powers. Okay, so let's see, we have sine x, then plus cos x gives us. So we will add this, we add this then to that. So we have here, I have 1, okay, I have 1 here, plus x, then I have minus x to the power 2 over 2 factorial, then I have minus x to the power 3 over 3 factorial, then I have plus x to the power 4 over 4 factorial, and I have plus x to the power 5 over 5 factorial, and I have minus x to the power 6 over 6 factorial, then I have minus x to the power 7 over 7 factorial, then plus in that sense. Pause. So okay, so we have this way. So we have, let's look out for e to the power I, then x, okay, or theta, which is equal to, now here, since we started from here, e to the power x is equal to this, 1 plus, then the power x, then plus this power x squared in that form. So we have 1, then plus x, okay, but this, look at my power here, I have I x, is that not so? So I have I x, then I have plus I x, then to the power 2, so this way to the power 2 over 2 factorial, like this, in that order, okay. So I have then plus I have I to the power x, that's I x to the power 3 over 3 factorial plus I x to the power 4 over 4 factorial, then plus I x to the power 5 over 5 factorial, then it continues indefinitely. Okay, so we have e to the power I x, which is equal to, we have 1, then plus I x, then plus, this is the same as I squared x squared over 2 factorial, because the power will affect each term. Then plus, I have I to the power 3, then x to the power 3 over 3 factorial, plus, then we have I to the power 4, we have x to the power 4 over 4 factorial, then plus I to the power 5, then x to the power 5 over 5 factorial, then it continues in that regard. So note this, from the beginning or the introduction to complex numbers, we learned that, from the introduction to complex numbers, we learned that I raised to the power 1 is the same as I. Then I raised to the power 2 is the same as negative 1. Then I raised to the power 3 is equal to this by this. Okay, so I have negative I. And I have I raised to the power 4 is the same as what? Positive 1. Then I raised to the power 5 is equal to I. If you are new here, can you visit my previous lecture videos on introduction to complex numbers, okay? I mean, I raised to the power 1240 is well explained, okay? So we have imaginary units way to, we have an extremely or big or large power or index. How do we simplify that? Everything is well explained under the introduction to complex numbers. So we are going to substitute stuff here. So wherever I see I put I there, I squared, I put negative 1 there, in that regard. So I have e to the power ix is equal to, I have 1, then plus I is the same as I raised to the power 1. So ix, then plus, look, we have I squared, but I squared is what? Negative 1. So I have negative 1, what do I have here? X squared over 2 factorial. Then I have here plus I cubed. What is I cubed? I cubed is what? Negative I. So I have negative I, then times x to the power 3 over 3 factorial. Then plus I raised to the power 4 is 1. So I have 1 times x to the power 4 all over 4 factorial. Then plus I raised to the power 5 is what? We have I times x raised to the power 5 over 5 factorial. It continues indefinitely. So we have e to the power ix, which is equal to 1 plus ix. Then I have negative 1 x squared over 2 factorial. Okay, so negative 1 is the same as what? I have negative what? X squared over 2 factorial. Then I have here, I have negative what? Ix over 3 factorial. Here I have plus 1 times x is x to the power 4 over 4 factorial. Then I have plus I times x is I x to the power 5 over 5 factorial. Then okay, so we have 1 plus ix minus x squared over 2 factorial minus ix what? Cubed over 3 factorial. Then plus x to the power 4 over 4 factorial in that sense. Now, what are we supposed to do over here? You realize that we have the real part. This is the real part. This is also the real part. This is also the real part. Why the real part? Because it has no imaginary part or imaginary unit. Once you have a term or expression with the imaginary unit, it makes it what? It makes this whole expression what? Imaginary part. So we have the real part and the imaginary part. So what we have to do is we have to group the real part at one side, then we group the imaginary part at one side. So this is the imaginary part. This is the ones with the I, those are the imaginary. This also contains I. This is also what? Imaginary. So let's do that. You have e to the power ix is equal to, let's group the imaginary part. Okay, so we have 1. Then the next imaginary part we have minus x squared over 2 factorial. The next imaginary part we have this, which is plus x to the power 4 over 4 factorial. We are done with the real part, right? Let's focus on the imaginary part. Now plus ix over, that's ix. Then the next imaginary part we have this minus ix cubed over 3 factorial. Then we have this plus ix to the power 5 over 5 factorial. Then in that sense. So we have this, right? So we can do this. E to the power ix is equal to 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial. Then plus, we can see I and I. So we can factor I out. So I have I, then we can do this. I have x here. Okay, then do this. I have x, then minus, I have x to the power 3 over 3 factorial. Then I have plus x to the power 5 over 5 factorial this way. Okay, so we have this and we have that. So what can we deduce from here? Now you realize that 1 minus this whole expression is cos x, and this whole expression is sin x. And you can see over here, this corresponds to this. So this represents the Taylor series expansion for cos. And this represents the Taylor series expansion for sine. So I can therefore say that e to the power ix is equal to, the whole of this is the Taylor series expansion for cos. Cos what? X. Then plus, what do I have? I can see I here. So I have I. And the whole of this is the Taylor series expansion for sine x. So I have sine what? X. Viewers, this is the proof. So I can say therefore e to the power ix is the same as what? Cos x plus I sine x. As simple as that. Now let's note something over here. Remember, in Euler's form or exponential form of representing complex numbers, we said that e to the power I theta is the same as what? Cos Here was x. That explains why here is x and x. So we have cos theta, then plus I sine theta. And we said that, okay, let theta, okay, equals pi. What happens? Say e to the power I pi is equal to, remember we said it's equal to negative what? 1. Negative 1. How? Why? Do you get it that way? So let's substitute. So I can say that e to the power I pi is equal to cos, wherever I see theta, I put what? Pi there, so I have pi. Then I have plus I, then sine what? Pi. So e to the power I pi is equal to cos pi is negative 1. I have negative 1, then plus I sine pi is 0. So I have e to the power I pi is equal to negative 1 plus 0, which is this. Now this is the same as e to the power I pi plus 1 is equal to 0. You get it that way? So viewers, this is a very important expression. So this is the Euler's identity formula. So now this Euler's identity exposes 5 mathematical constants. And this mathematical constant plays a key many courses, such as algebra, such as calculus, yes, and geometry. So let's look out for the mathematical constant here. We can see what? E here. So let me label this 1, 2, 3, 4, and 5. Okay, so I have E here. Let's come here. So we said this is that we have e to the power I pi plus 1 is equal to 0, right? So we have E here, which represents what? The Euler's form. That's the Euler's formula, okay, or the Euler's form, or the exponentiation. Then I have the I here. These are constant. I here is what? The imaginary units. Then have this pi, which is what? Our normal pi. They have 1. This 1 here represents what? Unity. So 1 unity. And we have what? Our this, which is what? The 0. As simple as that. So viewers, this is the end of the YouTube tutorials. We are going to explore and learn a lot. If you are not comfortable with the proving of the Euler's formula using the Taylor's series, you can visit my previous lecture videos where we've derived this expression without employing Taylor series. Bye.